Okay, it's recorded. Okay, so now we can officially start. Okay, so this is the last picture we saw yesterday, I think, if I'm not wrong. Okay. Did you find any problem with this? I don't know if you had time. Please. Mm-hmm. Okay, okay. If you look at what is written here, with 6.2 volts, you have a positive coefficient. Okay. Yes. Allora si sposta verso sinistra, quindi dipende come è disegnata. Lo guardiamo dopo con la slide. Okay. Okay, so this was, I told you, was the last slide, and chiudo il cassetto. Okay. The only problem with the circuit was that the output voltage was quite high. So I told you that maybe we need a smaller voltage in some circumstances. Okay. I forgot to push F5. Okay. Now we should see it better. What we can do in this case is to use a different circuit that is called the band gap reference. Actually, this version that I show you is very simplified. The real circuit may be a bit more complicated, but not that much. Basically, instead of this resistor on top, there may be a current generator, but with the resistor, it works the same. How is this circuit made? Well, basically, you have the power supply, VCC, a resistor through which flows all the current which goes to 1, 2, and 3 nodes, and also at the output if we take some current. The basic circuit is made by a sort of Widlar current mirror. If you remember, the Widlar current mirror is similar to a current mirror with Q1 and Q2, but we add a resistor R1 on the meter of Q2 in order to have a small voltage drop across R1. This voltage drop as a result that the two voltage base emitter voltages of the two transistors are different. In a simpler current mirror, the two transistors have the same VB. Here they have a slight difference. Usually the VB of Q2 is smaller than the VB of Q1. Due to the fact that the dependence of the current, collector current of Q2 is an exponential function of the VB, even a small voltage difference is going to give a very large current difference. Basically, Q2 will have a collector current that in general is much smaller than the collector current of Q1. That's what we saw with the Widlar circuit current mirror, sorry. That's the reason also why the whole circuit has been invented by Mr. Widlar itself. So once that he invented the current mirror, then he started to create a lot of different circuits. If you, maybe I already told you that if you look on Wikipedia for Widlar, there are a lot of stories about the fact that the more he drank, the better were the circuit that invented. So he had a serious problem with drinking. So when he drank, he invented a very nice circuit. He invented, let's say, half of the modern electronic integrated circuits. Okay, that was in the 60s, end of the 60s, the last century. No? And drink. Okay, so what is in this small box is also that this circuit is very interesting because actually it's not using any Zener diode. The Zener diodes are okay, but just because they use the avalanche phenomenon or tunnel, they tend to be very noisy. So that if you look at the output voltage with a good equipment, you will see that the output voltage is not, well, it is stable, but it has some small ripple at high frequency, a sort of white noise which comes together with the DC voltage. And also this circuit can work at very low voltages. Typical application are around 1.2 volts. That is very good for modern electronics. Why it is called band gap? Because it has to do with the band gap of the material. Basically, it has to do with the knee voltage of the device. So if we, instead of using silicon, we use gallium arsenide or other semiconductors, we will have different starting voltages, let's say. Okay, so if we have a look more in detail about this circuit, I told you that we have here a Widlar current mirror. The current mirror actually has two resistors, one on the collector of Q1 and one on the collector of Q2. Also, there is a third transistor, Q3, which takes the collector voltage of Q2 and in some way behaves according to this collector voltage. The transistor Q3 also controls the current drained by the circuit and basically is the one which regulates the output voltage VREF. If you look at this system, you can also see a sort of feedback. Why? In short words, if for some reason the VREF increases, this VREF increase will increase the current through Q1. The current through Q1 has to do with the resistor R3. It will increase the current through Q2. It will decrease also it will change the voltage in the base of Q3, and so the system will tend to stabilize more or less itself. But now we are going to see how actually the output voltage is generated. We have to follow this path here. The VREF actually is the collector voltage of Q3. But if you remember, usually we cannot say what is the collector voltage of Q3 just looking at the transistor by itself. Usually when we have a circuit like this, we must determine the collector voltage of Q3 looking in some other way. The other way to look for is consider the path through R2, so the voltage drop through R2, and the VBA of Q3. So actually the VREF can be expressed as the sum of I2 R2 plus the VB of Q3. So that's the path to follow. Again, in absolute, we don't know at the beginning what is the voltage of the collector of Q2. So the only way to calculate VREF is through the voltage drop across R2 and the VB of Q3. And that's what I wrote here. Again, for studying in an easy way the circuit, we will neglect all the base currents. So we'll say that the base currents are absolutely negligible. Basically, if you have a transistor with a high Q, something like 100 or 200, most of the time we can do that. Now, okay, so we know that the VREF is given by this expression, but we can say that more or less the VBA of Q3, sorry, should be something around 0.7 volts. Let me take the laser pointer, okay. So this voltage here, VB Q3, should be around 0.7 volts. But we don't know how much is the voltage across the resistor R2 unless we calculate the current I2. And that is what we are going to do now. For calculating the current across I2, we can observe that this current, I2, is the collector current for Q2, but it also is basically the emitter current. We are neglecting the base current of Q2. So we definitely must have a look at this combination Q1, Q2. And I already told you that if we consider the difference between VB Q1 and VB Q2, this voltage difference will be the voltage drop across R1 that in turn is given by R1 times I2. Okay, the current is the same. I forgot to take the pen with me, I can write it like this. So the current here is again I2. Okay. Well, I'm interested in the difference between VBQ1 and VBQ2. I can write it as I told you. VBQ1 minus VBQ2 is equal to the emitter current Q2, that is the current I2 times R1. And that's it. However, now the problem is, okay, from this expression we can calculate I2 if we know VBQ1 and VBQ2. What can we do now? We have to remember the constitutive equation for the transistor, for a BJT. In a BJT, the collector current can be expressed as a current IS, that is a very small current, that is a sort of, in the diode it's a reverse current, in the transistor it is called a scaling current. Typically something around nanoamps or even less. And this current, which is a constant, can be multiplied by the VB, so the base emitter voltage of the transistor, over VT. VT is the so-called thermal voltage. The thermal voltage, if you remember, is KT over Q. Okay? So, in this equation here, in this part here, instead of VT, I wrote KT over Q. K is the Boltzmann constant, T is the temperature in Kelvin, so the absolute temperature, Q is the charge of the electron. 1.6 times 10 to the minus 23, if I remember. Don't ask me the Boltzmann constant, I don't remember, okay. So that's for sure. But we know that at room temperature, KT over Q is 0.026 volts. So it's 26 millivolts at 27 degrees, which are 300 Kelvin degrees. That's one of the few things that we must remember in life. We can forget many others. Okay, so why did I write this? Just because I wanted to convert this equation and derive an expression for VBE. If I move IS on the first term, then I pass through the logarithm with the E basis, I get VB as a KT over Q, the natural logarithm of IC over IS. Okay, so this gives me, which is the base emitter voltage that I need if I want a certain IC, collector current for the transistor. I can write this expression for both transistors. So VBQ1 minus VBQ2, and I get KT, natural logarithm of IC over IS minus logarithm of IC minus IC2 over IS2. All that difference should be equal to I2 R1. Okay. Now I can simplify a bit this expression. First of all, the difference between two logarithms is actually the logarithm of the ratio between the two arguments. Moreover, if I suppose that the two transistors are the same, they're equal, they will be integrated. So take care to have two transistors which are more or less perfectly equal. I can, when I take the ratio between these two terms, I can cancel IS1 and IS2, which are the same. So what I get at the end is, I just reversed this expression, I2 R1 is KT over Q times the natural logarithm of IC1 over IC2. And that's it. So if I know IC1 and IC2, I can determine how much is I2 and put it here. Well, I still need some trick. Otherwise, it's not easy to in absolute, I could calculate the I1 if I consider that the I1 is Vref that I don't know, minus 0.7 divided by R3, but that's not the right way to go. Now I can do instead a different consideration. Basically, I need to know IC1 and IC2. What are IC1 and IC2? They are I1 and I2. They are the collector current of those two transistors. I can observe that if I wonder what is the voltage on the collector or Q1. So what is the voltage on the collector of Q1? The voltage here on this node. Well, more or less, it's VB Q1. That is around 0.7 volts, okay. What is the collector voltage of Q2? If I look here, well, we know that the VB of Q2 is not the same as the VB of Q1. And then also, there is also, sorry, a voltage drop on R1. So I'm not sure what is the voltage here. But if I look on the right, I see that again, this is also the base voltage of Q3. So I can say that for Q3, more or less, it should be 0.7 volts. So if I suppose that the Vref is much higher, I can say that basically the voltage on this node and on that node are the same. Due to the fact that those two resistors, R3 and R2, are connected on top to the same node, so they have the same voltage, and on the bottom they are connected to two nodes with the same voltage, I can say that the voltage drop is the same on the two resistors. So I can write that I1 R3 is equal to I2 R2, more or less. It's an approximation, but it's good enough. We must go. We must approximate, otherwise, if you don't like approximation, we use the simulator. Okay. Okay. Someone will ask me, why did you call this resistor R3 with current I1? I don't know. I just took this picture from a book, so it's not mine. Now, this is a sort of data sheet from On Semiconductor. This was very nice for this part of the description. Okay, so I can write I1 R3 is more or less I2 R2, and so I can solve in I1 over I2 is equal to R2 over R3. But I1 and I2 are IC1 and IC2. So I can take this inside the relationship here. Again, with some approximation, instead of IC1 and IC2, I can place R2, R3 here. Then, from this expression, I just take R1 and bring it down, and I get I2 is equal 1 over R1, KT over Q, the natural logarithm of R2 over R3. Okay? That's the answer to calculate with some approximation the current I2, which is the collector current of this transistor, but also is the current which gives some voltage drop on R2. So I can use this term in this formula here, and what I get is Vref is equal to VBQ3 plus, I still have a term R2, so it becomes R2 over R1, KT over Q, natural logarithm of R2 over R3. Okay. That's our result. So we were able to calculate the voltage reference. And I just want to go back to this one. I wrote something strange here. If I have a look at this relationship with some approximation, I'll discover that this term I2 is a current which has here a constant, 1 over R1, logarithm of another constant. Not only, this constant R2 over R3 must be larger than 1. R2 must be bigger than R3. Otherwise, we'll have a negative number. What I'm saying? No. We'll get a negative logarithm, and so we'll get a negative current, which is not very nice. So that's one reason more for having this resistance R2 larger than R3. It must be like this in our design. The other interesting thing, again, is that in this expression, we have constant everywhere, R1, K, Q, this logarithm, but we have only one variable, T. T is the absolute temperature, the temperature in Kelvin degrees. Well, this means that this term I2 is proportional to the absolute temperature in Kelvin. Okay? This current is proportional to the absolute temperature. And this is due to the fact that we have, in some way, this current mirror here with a sort of feedback through the transistor Q3, which locks the output voltage. Apart from what we are going to do now, having a current which is proportional to absolute temperature, and that's why it is called with its acronym PTAT. When you talk about a PTAT generator, it's something which uses this. This term alone can be used for making a very nice thermometer. Thermometer, the one for measuring temperature, okay. The old mercury, okay. Okay. So when you buy a chip which is used for measuring the temperature, probably it will work on this principle here. If we have time, I will show you a nice simple circuit which is called the LM35. I don't know if I told you. LM35, it's used a lot when you play with the Arduino and stuff like this. It costs nothing, €1 just if you buy one. They will give you just like this. So it's very cheap, which has inside this circuit here. Basically, if you want a voltage proportional to the absolute temperature, you just send this current to a fixed resistor. And so you can convert a current into a voltage. That's what the LM35 does, basically. It gives you a voltage, is more or less 10 millivolts per Celsius degree. Okay. Obviously, this is correct if we suppose that all the transistors are working. Working, funzionano. You know that if you cool down a semiconductor, you will not have the thermal generation of charges inside. You will not have also the ionization of the doping. So usually this circuit gives a temperature which is proportional to the absolute temperature, but usually starting from minus 50 degrees up to 125, 150 degrees. Because if you heat too much a semiconductor, a doped semiconductor, due to the thermal generation of the electron-holes couples, when the temperature is too high, you will mask the doping. So you will have more carriers generated by thermal effect than the carriers which are due to the doping. At that point, the transistor will not work anymore. So that's the problem with the template. If you look at the specification, typically you can use this kind of circuit between minus 50, minus 40 to plus 125, something like that, depending if they are industrial, military, or civil, commercial specification. For commercial specification, usually you go from 0 to 70 degrees. They are the worst circuit that they sell you for nothing. But if you want the military version, you have to pay much more. So, okay. They are very selected circuits. Okay, so for free, we got also this nice circuit here. If you want to use, you can use that. I go back to this circuit here. So the final solution, Vref is equal to this expression. We wrote this expression just by analyzing the circuit. But this is the formula that we can use for designing the circuit. If we want a definite VREF, we can choose what? Well, the temperature is more or less room temperature. We can choose R1, R2, and R3 to get the voltage that we want. So basically, we don't have limitations. There is another point. Well, we know that usually we must take care of what? In a voltage reference, we must take care of the VCC, the input voltage, the output current, and the temperature. Okay, we already studied those two parameters. Okay, if this is the final result, it looks like it has no dependence on the VCC. So it is very stable with the VCC. Actually, there will be a small dependence due to this resistor. If you want to increase the range, most of the time you just remove this resistance here on top and you put a current generator. The current generator gives you a fixed current which does not depend. No, okay. Okay, no, non è piccino, okay. No, for some reason the picture disappeared. Chi è il santo protettore dei PC? Non lo so che cosa. Accendiamo un cero al santo protettore. Okay, so we can choose the voltage that we want. I was saying something. Okay, we have no dependence on VCC. If you use a current generator here, again, it looks like there is not much dependence on the output current if the output current is small, because basically, if there is a variation in the current that the system absorbs, probably this transistor Q3, which is in some way in feedback with the whole circuit, will adjust its collector current in order to adjust the output voltage. So we can take some of the current. Actually, the output current should come through this resistor. So we must be accurate. Usually, again, if you don't want any problem with the current, we just connect this circuit to a high impedance buffer. So we don't have problem. Voltage buffer. So the circuit works with no output current. What about the temperature? Well, here we have a problem because actually the VB or Q3 is changing, but also the T in this term is changing. So definitely the system changes the output voltage with temperature. Okay, but we know that if we are interested in the variation of the reference voltage with temperature, we just want to calculate delta VREF. Delta is an expanded version of the differential of function of the VREF calculated on the temperature. So if you take the differential of this function based on temperature, we get that the variation of the reference voltage is equal to the variation of VBQ3 that we already know. It's minus 2.2 millivolts per Celsius. Plus this term here, where everything is fixed, we just have the delta T, the variation of the differential of the temperature, let's say, the delta T. So if we know that delta VB is minus 2.2 millivolts per Celsius degree, why don't we adjust the resistance R1, R2, and R3 in order to get a positive variation of this term of plus 2.2 millivolts per Celsius degree? Okay, delta T is 1 Celsius degree, for instance. This term for 1 Celsius degree will decrease by 2.2 millivolts. We must adjust all the resistance in order that we have plus 2.2 millivolts per Celsius degree by the whole term here. Okay. Now we see that actually we were able to write two equations with three variables. This means that we still have 1 degree of freedom to be free to choose a combination of three resistors that will satisfy both requirements. So you can decide the output voltage and have a stable system. what we do is just write this expression, and instead of delta Vref, we put 0. I don't want any variation with temperature. So, and I can get this equation here that must be satisfied for having 0 variation in temperature. Okay? Sì. No, it depends. You mean this part here is varying. It's varying. Okay. But here we want that it varies. Okay. Okay. But those are two different applications. The first one is for making a thermometer. Here instead we want a stable Vref. So here we must compensate what? Basically, this term here has been added to the VBA of Q2 or Q3. The VBA of Q3 is basically the bang gap. It's linked to the bang gap of the semiconductor. If you remember, usually this VB is a direct bias of a diode, and which is 0.6, 0.7, which is smaller than the typical bang gap for silicon, which is 0.8, 0.9. No? So there is a relationship more or less on the bang gap of the material and on the knee voltage of a diode made with that material using a PN junction diode. Okay, so that's why we are talking about band gap reference, because usually the two terms are more or less of the same order. That's why I told you that if we have a VB of 0.6 volts, the other term will be more or less that much, and so we have a Vref of 1.2 volts, 1.4, something like that. Okay. So we can play a lot with those equations and have a reference voltage which is stable in terms of VCC, output current, and temperature. Obviously, what I told you is true if we have all those formulas with all those approximations. In the real world, it doesn't work like this. Usually, if you design a circuit like this, you will do what they call a corner simulation. So they change the temperature between -40 to plus 150, and they see how the output temperature will change. This is something that we can try to do in simulation as well, and see how stable it is. So it will tell you, for instance, you have 1% variation on the output voltage in this range, or 0.1 if the range is smaller. Don't go over those corners, otherwise the system will be much less stable. Okay. And that's something that is usually done. So also, if you take the data sheet, you'll see a curve like this. It's quite flat and then bends like this, or it goes up, and depends. Well, once you catch the mechanism, it's quite easy. Those are simple formulas that probably we already saw when we studied with our current generator. They're the same, just rearranged in some way. I have to see something more about the circuit. Prego. Hello.
Io non ho capito una cosa. Quindi la delta VBE Q3 dell'ultima espressione, quella in basso, è, diciamo, è dovuta al fatto che a causa della temperatura varia la VBE, no?
Sì.
Quindi noi dobbiamo fare in modo che con il materiale che utilizziamo per il transistor questa vada a compensare la differenza di temperatura del secondo termine.
No, okay. So your colleague is saying we have this variation VBQ3 due to the transistor. Can we say change the material for compensating? No, it's not this point. The material, the transistor is that one. You cannot compensate this. You compensate the variation of VBQ3 just compensating, adjusting the current I2 using this part of the circuit here, okay? This expression is the expression of the current I2. The voltage reference is the sum of this part plus this part. This voltage is going down when we increase the temperature, so we need to increase a bit the current I2 to compensate the variation with this voltage here, okay?
Okay.
Okay. No,
Quindi,
the material, you cannot do anything.
Quindi agiamo sulle resistenze.
No, due resistenze. Abbiamo due contributi di questa tensione più questa. Qua sotto. Ok? No, se ha qualche dubbio... Ok. So this circuit, I can tell you, is very popular. Everywhere we need a voltage reference. Now we will find this problem. There is something a bit complicated that I will try to explain. I'm not sure if I will succeed in explaining how it works, but what is the point? The point is that if we again take a look at the circuit, there may happen strange things when we turn on the circuit. Turn on, we power on the circuit. Basically, if the circuit is off and then we switch on the power, you can imagine that the VCC, the voltage at the input, is not going up like a step, but is slowly increasing. In the real world, the absolute steps does not exist. There are always parasitic capacitance, what you want. So when you turn on an equipment, the voltage will go up. We can suppose like a ramp, for instance. That's the easiest way to suppose. Just a moment. What is this graph? We'll go there. This graph here represents the voltage on the collector, or Q1, that is increased from 0 to the right, so it's increasing, and the voltage on the collector transistor Q2, here. Okay. So what should we see if we take the VCC voltage and we increase it from 0 to the working voltage, let's say 5 volts, I don't know what, okay? We can imagine that this voltage is increasing like a ramp, just to concentrate on what's going on. So if the VCC increases, I can imagine that also V1 will increase. Basically, V1 is related to VCC unless if you consider that there is some voltage drop on this resistance and this resistance here, okay? At the very beginning, when the transistors are basically off, so when the input voltage is below 6.7 volts, I would say 0.6 volts. So let's suppose that the VCC is going up from 0 to 0.6 volts. All the transistors are off because we did not reach still the threshold for the diode. This means that the voltage on V1 and on V2 are the same because there is no current anywhere. And so we have this line that is around 45 degrees. This line at 45 degrees means V1 and V2 are the same. Okay? This is sort of input-output characteristic, let's say. There is no time here. It's only the voltage on the collector of V1, of Q1 and Q2. So at the beginning, we increase the voltage of V1 because we are increasing VCC. There is no current I1, I2 anywhere. And so we can suppose no voltage drops on the resistances. And so the voltage of V1 and V2 are exactly the same. Okay. This line has a 45 degrees still, angle. 45 means same voltages. Okay? You studied the parametric graph, something like a parametric expression. Also, Lisa showed a picture. I don't know if you've done that. Anyway, well, the voltage of V1 is going up. But here, something strange happens on V2. When the input voltage reaches the VB on 0.6 volts, transistor Q1 starts to conduct. Also, transistor Q2 starts to conduct. The currents are still very small. If the currents are small, I can say that the voltage on R1 is small, and so maybe the voltages on the two collector when the current starts to flow are still the same. we are still in this part, we are a bit over the VB on, but the curve is still almost at 45 degrees. But when the current continues to increase, what happens is that due to the fact that R2 is much larger than R3, you remember I told you that R2 must be much larger than R3. Otherwise, we have a negative logarithm. We more or less have the same current in the two transistors, but the voltage drop on R2 becomes much larger than the one on R3. It can be so large that the voltage on the collector of transistor 2 goes below 0.6 volts. So the transistor Q2 gets into saturation. So we have more or less the same current on the two transistors, but the voltage on R2 is much higher than the voltage on R3. And so the collector voltage of Q2 goes down below the threshold, and so transistor 2 saturates. And we are here. And then, if we keep increasing the voltage, the current on transistor 1 will go up and up. Also, the base voltage of transistor 1 will go up. The current in transistor Q2 tries to increase. It will increase the voltage on R1. There will be a larger imbalance on the two voltages, which reduces again the current on transistor Q2. So the transistor Q1 pulls up in some way the voltage on the base of Q2. This increases also the emitter voltage and also the current on R1. So there will be, in this case, the VB of Q2 will be much smaller than the VB of Q1. This reduces the collector current. And so probably the transistor Q2 will be again pulled out of the saturation. We are here. I know that it's a bit complicated. I will give you a couple of copies where this is more or less explained, but not much differently than what I'm saying now. So, what it may happen that the voltage on the collector of V2 goes up again. Okay, so if I scan the voltage on V1, I'll probably get this strange curve as the voltage, the collector voltage of Q2. Why are we interested in this? If I take a line VB on, this function crosses in 3 points the VB. Okay? Why is that important? Because to the collector V2 is connected also transistor Q3. Well, all the stuff that, all the design that we did before is related to an operation point where both transistors are working in their active zone and also Q3. So all the hypothesis that we did when we calculated the previous relationship on the previous slide, where if Q1, Q2, and Q3 were in their active zone. So we are interested in a place, in a point like this. Here, all the three transistors are in the active zone. But there is also one other possibility. If, when the voltage VB goes up, when the collector voltage of V2 goes up, the collector voltage of V2 reaches the VB, the transistor Q3 can turn on. If Q3 turns on when the voltage on V1 is small, probably this transistor Q3 will drain all the current, and so the increase in VCC will not propagate here. Basically, the danger of this circuit is that when you turn on the system, there is a chance that the system locks here instead of here. So we'll not get an output voltage that is Vref. You will get something which is probably close to VB, 0.6 volts. Why? What we did in the past was designing the system for this point here. a condurre qua. If Q3
la tensione di P2 diminuisce come se dal grafico, ma perché quella di V1 aumenta?
No, quella di V1 non può aumentare perché la corrente di V1 è data da questo percorso. Se il transistor Q3 comincia a condurre, si tira tutta la corrente e non può più, quindi questo è quello che aumenta se noi, ecco, ok, you're right. This graph is made if we don't have Q3. That's the hypothesis. Okay, this graph is made if we don't have Q3. If we have Q3 instead, Q3 can turn on either here or here. No, you're right. I should have written this. This is actually the graph only for this part, V1 and V2. Okay. So the danger is that the system will lock here. And so this is called as the startup issue. And the only thing that we can do is try to delay the turning on of Q3 until the system reaches this point here. Okay. Basically, there are two ways to resolve this. You can put a sort of low-pass filter on the base of Q3 with a very long time constant. So when the system turns on, it takes some time before Q3 turns on, just because there is this delay in the base of Q3. Or you can consider a different circuit placed somewhere that will give a kick to the system in order to move it from here to here. So if it's sort of a kick to the system that you can plan with other part of circuits. But if the system is already here, or if it is locked here, you just push some currents on the base, for instance, of a transistor Q1 in order to move it from that situation. So this sort of kick-off circuits are usually designed when in the band gap references. Do you want to close a little bit? C'è un po' di vento? Ah, di qua, ok. Ma io pure sto volando, preferisco. Okay, sorry, there was some wind here. So that's a problem, and that is the reason why the true band gap reference circuits are a bit more complicated than what I'm showing here. There is another option. Once that we are in the range of integrated circuits, having one or more transistors is not costing anything more. So instead of having only 3 transistors, we may decide to use an op-amp inside the circuit. Maybe we have 10 transistors here, but the cost is basically the same. The solution with the op-amp is very interesting because actually, if we do some simulation, we will find that there is still some dependence of the output voltage in the circuit on VCC. So the circuit is actually a bit influenced by the VCC in terms of output voltage. While if we use as the, let's say, feedback stage, instead of Q3, we use this op-amp, the op-amp is intrinsically not depending on the power supply of the op-amp itself, okay? So we have a much more stable circuit if we change a bit to things like this. Now it's interesting to, actually this is the most, more modern version of the circuit. We can imagine that we have an op-amp with a very high gain, like all op-amps. And the output voltage, Vout, is this. Obviously, everything is referred to the ground. Here they didn't put the ground. We can put the ground here, for instance, like this. Okay, so that's the ground. Okay, let's suppose that's the ground. So the output voltage is the output voltage of the op-amp itself. This voltage is also used more or less like it was here to supply voltage to R2 and R1. These two resistors here are sending their current to transistor Q2 and Q1 that are both connected as a diode. They are both with diode connection. There is also a resistance R3 in series with Q2. But what isn't interesting is that due to the fact that in some way there is a negative feedback in the system, the output is connected here, and this goes through the negative input. If you remember, every time that we have an op-amp with feedback, we automatically can say that there is the virtual short circuit between the two inputs. Okay? So this means that the voltage on the negative input is the same as the positive input. We don't know how much it is, but we know that it's the same. If the voltage on the two inputs of the op-amp is the same, and this is the output voltage, again, the two resistances R2 and R1 have the same voltage drop on their terminals. You know, because the two resistance R1 and R2 are connected to the same voltage on the top and to the same voltage on the bottom because there is a virtual short circuit between the inputs. And so we can start writing I1 R1 is equal to I2 R2. So we start here this time. Okay. Then we can calculate how much is the Vout. We can write, for instance, that the Vout is equal to I1 R1, this voltage here, plus VB Q1. So in this case, we take the easiest connection. The output voltage is I1 R1 plus VB of Q1. Q1 is connected as a diode transistor, okay? And so we can write I1 R1 VB Q1, and due to the previous relationship, we can also write I2 R2 plus VB Q1. But, see. Yeah, the supply is connected to the op-amp. There we can write, there will be two wires. One is VCC, only out to the op-amp, yes. The other voltage could be even ground. It is not necessary that we have a negative voltage. Just because all the output voltage are positive, we can use also a good op-amp with the ground here. Okay, no problem. It should work right the same. And like that. So now we want to calculate how much is I2 R3. How much is I2 R3? Well, due to the fact that the voltage in this node is the same as the voltage on this node, we can see that the difference between this point and that point of R2 is simply the difference between the two VBs of the two transistors. We could also write that the voltage VBQ1 is equal to VBQ2 plus I2R3. These are the same voltages, so the voltage here, VBQ1, is the same as the voltage VBQ2 plus I2R3. That is this one. So basically, this is the same relationship as we saw before. KT over Q, logarithm of IC1 over IC2. Again, IC1 and IC2 are related to R2 and R1. So we can use the same formulas. And so we end up with this formula. Vout is equal to VBQ1 plus R2 over R3, KT over Q, logarithm of R2 over R1. We can work exactly in the same way as before. Consider the variation with temperature and change, and also obtain a relationship for choosing in the right way all the three resistances. So it's exactly the same formula. But the good point now is that this circuit is intrinsically more stable than the previous one because the output voltage does not depend on the VCC. The VCC only goes to the op-amp, which is very stable. Also, we can imagine that we could take some current from this op-amp because in a good op-amp, the output the voltage is equivalent to a real voltage generator with a very small, theoretically null series resistance. So the output resistance of the op amp is very small, in theory it's 0, and so we can take some current from this circuit. It's not like the previous one, which was very delicate. So that's the setup that most time you will find in a real system. There is one question that actually I don't know how to answer. Has this circuit the same problem as the previous one? Well, same problem, the startup issue. Well, I can't tell you. I didn't find any note about this. So I should look for different books. And probably it doesn't have the same problem. Because in some way, there are two transistors which are separated from the output. But I have to investigate more in that. If you find something, please let me know. I should find a different textbook. This was taken from the Gray Mayer. It doesn't say anything. It just changes the pages. Say, okay, that's it. So, but I can ask my colleague at the ST Microelectronics that they work all the time with this. And I should do that next time I meet them. Okay, what time is it? Do we want to do a short pause? Same. 3 minutes? No more? 5 minutes? Okay. So I'll see you in 5 minutes, okay? Okay, just we stop for a while. Okay, so we are back. What time is it now? 22 past 30. Okay, so let's go back to this talk. Do you have any question about the circuit here? From home? Nothing. Okay. Well, now I go back to where everything started for some strange reason. Why I'm going back? Because what we have seen in the last slide were three possible circuits to be used as voltage references. So the point was, we want a very stable voltage. How can we do that? And we saw that we can use a Zener diode. We can use the constant current generator, the one with the two transistors, or the band gap reference. I told you most of the time, if you want to use this like a voltage reference, we are not going to take any current from the voltage reference circuit. So they are used without any current. Now we want to move to a different point of view. I want to make a stabilized power supply. So I want to take current from this power supply. What kind of circuit can we use? Well, actually, the first answer is you can use also a Zener diode as a power supply. So you can take current from the Zener diode. Now, what I want to show you is, okay, I can take this current, but how much current can I take? And how good is going to be this power supply, which is made with only a Zener diode? Okay, that's the reason why I plotted again this circuit. It's exactly the same picture. We have VCC, the resistance R, which is the biasing resistance, and the Zener diode here. In this part, I did not put in evidence what is in the equivalent model. I just placed the Zener diode. Also, for my convenience, I rotated by 180 degrees the plot that we saw before. So now in the first quadrant, we have I reverse and V reverse. This is exactly the same plot that we saw before, but has been rotated. And instead of having minus V minus I put I reverse as the opposite direction than the direct current. So for me, I reverse is the current. That's something that I should have done. I reverse is the current flowing in this direction now. Okay? I rev. It's hard to write. Rev, something like this. Then I'll adjust this picture. So I reverse is the current which is going in the reverse direction for the diode. Okay. V reverse is basically the voltage, the reverse voltage, so the voltage that appears at the Zener diode. And the characteristic of this Zener diode is given by the blue line. This is a very simplified version, okay? So we remember that if the reverse voltage is below VBZ, the diode is not in breakdown zone. Only if we go over VBZ, the diode will go into the breakdown situation. That is this blue line. Now I want to see what happens, for instance, when I just measure the output voltage without any load. So now let's suppose that we have no load resistance placed here. Okay? No, there is no RL. If there is no output resistance, we can say that basically VCC pushes some current through R, and it is the same current that goes through the Zener diode. So it's what we call the I reverse current. If you want to draw the load line, that is the red line here, we can simply consider the VCC in this point here. That's the open voltage, the voltage with no diode, let's say. Then I told you we consider the maximum current that can flow here if the diode was a short circuit, and we get this VCC over R. You remember? And then we draw the line from here to here. So if we don't have any load, we can say that the operating point for the diode is this one, which corresponds to a certain VZ, that is the output voltage, and a certain current here. The current here is basically the current, the I reverse that is flowing through the diode. Okay. The first consideration that we can do, no, maybe you can, I'll do that later, it's safer. Okay. Now I want to calculate what happens if I connect a resistance RL to the output of this circuit. I forgot to take the pen with me. There is a very simple way to calculate how things change if we connect a load resistance at the output. The easy way to see everything is just to mentally swap, invert the position of the Zener diode and of RL. So we are interested in the output voltage, VZ. It doesn't change anything if we take the resistance to the left and the Zener diode to the right. So what we get is something, let me see if I can do that with the mouse. I forgot the other pen. So what I'm saying is basically to have something like this. The resistance R, then the resistance RL, and here I put the Zener diode, like this. Okay, and here we have a ground. Okay, it's very hard to plot, okay. So I just inverted the two positions, and I want to see which is the output voltage here. That's a VCC. Okay? I've not changed anything. But now I see that actually I can consider this part of the circuit to the left, and this is VCC. So those two resistors, one is R, the other one is RL. It actually represents a voltage divider. And I can calculate the Thevenin equivalent for this voltage divider. That's what I've done here. You see, I placed instead of VCC and those two resistances, R and RL, an equivalent circuit according to Thevenin. V equivalent, R equivalent. And the Zener diode. Come? Now if I see that those two resistances are, no, it's sorry. Okay. They make a voltage divider. So I can calculate the equivalent Thevenin circuit for this voltage divider. That's the equivalent circuit. How can we calculate? The equivalent voltage is simply the output voltage with no load of this voltage partitioner. So how much would be the voltage here if I take off the Zener diode? VCC times RL over RL plus R. That's just a voltage divide formula. And that's the V equivalent. Do you remember what is the equivalent resistor? Simply the parallel of IR and RL. And that's the formula. Equivalent resistor RL times R divided by RL plus R. Now, I have a new circuit where the VR, the Zener diode is the same. So I can use the same line here. Same characteristic for the Zener diode. But I have to change V equivalent and R equivalent for drawing the new load line. Okay, what is the intersection of this new line with the horizontal axis? Well, it will be V equivalent. That's number here. What is the intersection with the other curve? It is V equivalent divided by R equivalent. That's the ICC, the short circuit current, so the other point. So V equivalent over R equivalent. I use this formula, VCC times RL over RL plus R, divided by the reverse of this, RL plus R divided by RL times R. If I remove what I can take off, I will get the VCC over R. So the interesting point is that when I add an output resistance, I can recalculate the load line simply moving the output voltage from VCC to V equivalent, the power supply, the supply voltage from VCC to V equivalent. But this point here, the intercept with the current axis will remain the same. So we get what we would call in Italian is the stella di rete propria. So come si chiama? Un fascio proprio di rete, esatto. Cioè l'improprio era una rete parallela, il fascio proprio erano quelle che facevano centro. So all the load line will start always from this point here. And what we changed is only the V equivalent. For instance, if we increase to infinite RL, if we increase RL to infinite open circuit, we will go back to VCC because RL over RL plus R becomes 1. So again, this point moves to the right to VCC. While if we reduce the RL resistance, we are simulating a load that absorbs some current, this curve will move to the right. What is the worst situation? If this point, V equivalent, goes below VBZ, we lose any regulation. Because we have a line like this, and here, the Zener diode is no longer in a breakdown situation, so it's not stabilizing. We can also see actually that if we have a variation in the output current, we are varying the value of RL, the equivalent voltage will go down. But we see that actually the output voltage of the circuit will go down a bit, will change a bit. The change in the output voltage of the system is due to the slope of, to the dynamic resistance of the Zener diode. That's a concept that we already saw somewhere. The variation in the output voltage is linked to the dynamic resistance of the diode. Okay, so if we reduce the value of RL, that means that we are taking more current, and if we take more current, we move to the right, to the left, and so the output voltage will decrease. If we try to take too much current, too much means we can calculate how much is the limit. The system will lose regulation, the diode will not be anymore in breakdown, and so the output voltage will drop enormously. We can just, if you want to know, for instance, which is the maximum voltage, maximum current, we can just move this V equivalent to VBZ from the formula and see what is the maximum current. So it's just a matter of making some calculation. So, in short words, if we are in a situation where you have no load, all the I reverse goes here, and that's the maximum current that's the current which will go in the Zener diode. Basically, if you try to draw that current from the load, what will happen is that you are taking all the current, you are not sending any current to the Zener diode, and so the diode goes into, comes out of the breakdown region. So more or less, the maximum current that you can draw from this circuit is the bias current of the Zener diode when there is no load. Bias, la corrente polarizzazione of the Zener diode when you have no load. Okay? That's something. This means also that this circuit here is very inefficient. It is called, we will see the difference, a parallel regulator. It works in this way. The output voltage is given by the VCC minus a voltage drop here. If you want a very stable output voltage, the current through this resistor must be kept constant. This means that if you have no load, all the current will go through the Zener diode. If we have a load, a part of this current will move to the load, a part to the Zener diode, but the total current will remain the same. Current flowing through here will remain the same. This means that this is not a good circuit, for instance, for powering a cell phone. If in a cell phone there is a stabilizer like this, it means that the battery will be discharged even if you're not using the cell phone. So this is not an efficient way to use it. Actually, you will find this kind of circuit only for very small supplies. So if you need something that you are sure that is always connected, and probably that draws a very small current. So even if you have a constant power dissipation, you don't care because the power dissipation is just nothing. It's negligible. So this is an idea for doing a stabilized power supply, but is almost useless. It takes power, it draws power, even if you don't have any load. And that's typical for the parallel configuration power stabilizer. Actually, you can find also circuits which are more powerful of this. And just have an idea. In a simple way to stabilize the power coming out from the solar panels, photovoltaic panels. Let's suppose that you have a photovoltaic panel attached here, and the load in our case is the battery that we must charge. Usually they have a parallel regulator which takes into account what is the voltage on the battery. When the battery is discharged, all the current will go to the battery, and the power regulator doesn't take any current. But if the battery is too charged, it's charging too much, and you keep sending current, it will destroy the battery. So in this case, we have a parallel regulator that takes and wastes current, but we don't care. The power from the solar panel is free. It's for free. So it's better to waste that power than killing the battery. That's why most of the time you will see a parallel regulator that controls the voltage on the battery of a photovoltaic panel. Okay. That's a typical application for parallel stabilizer regulators. That's the reason why, again, here I schematized the concept and the difference between what we have already seen, the parallel regulator, and the series pass regulator. That's the next step for us. Again, in a parallel regulator, you basically have an input voltage. You need the bias resistance. This resistance is for biasing, but also is the resistance where you can regulate the drop, the voltage drop, in order to stabilize the output voltage. Here I used a variable resistance that is controlled by feedback system. The feedback system checks the output voltage, and if it doesn't like it, it just changes the resistance of this regulator here in order to keep the output voltage constant. Basically, in a Zener diode, all this part is the Zener itself. Okay, everything, the Zener works like a feedback system. It's simple feedback system, but basically in application like the solar photovoltaic panels, we have a real circuit which does the feedback and also a variable resistance. A variable resistance basically is a transistor, which changes the current that can absorb in order to keep the output voltage constant. But as I told you, this is very inefficient. Yeah. Just a few notes. There is a constant power that is drained from the battery, but if we have or we don't have the load, and also the maximum dissipation, this element here, the regulator element, is when we have no load. This means that this circuit, this component here, will heat a lot. So we must dissipate the power. Okay. So this is very inefficient, and usually it's not used unless we have a particular application like what I told you. The other approach instead is of having a series pass regulator. In this case, we can have this series pass element here, the load here, and we keep the output voltage constant just because we can make a sort of variable voltage partitioner that basically we can regulate this element in order to keep the output voltage constant. So we change, thanks to the feedback system circuit, we change the output voltage just changing the resistance of this regulator. It's again a voltage partitioner, R1, R2. For instance, if we don't have load, we must bring R to infinite. So we open this element here, and the output voltage will be fixed. It can even go to 0. Okay. Usually, in a real system, you need to always place a small resistance in order to keep the partitioner, even if the load is not there. A small or a big resistance. You need some resistance in order to close the circuit to ground. Okay. But in principle, if you don't want output voltage, you just remove open the circuit. One way is this, to have a collector and emitter here, a voltage follower. We will see that quite soon. So while if the load tries to drain current, probably the output voltage will decrease, and so we reduce the resistance of this regulator in order to keep again the output voltage constant. Okay. In this case, you see that actually you are consuming power only if the load is attached. Then we have to do some calculation about how much dissipation we have here or here. In general, for a given current, the higher the input voltage and the lower the output voltage, the higher the dissipation here. Because the difference between V out and V in must drop all on this element here. And this is a transistor, basically. So we must take care that the power dissipated in the transistor under given situation is not too much. Otherwise, we can destroy the element. Okay. Let's see what I wrote here. So minimum dissipation when there is no load. Oh, that's good. All the current drained from the battery goes to the load, so we don't waste current. We waste power. We don't waste current. We waste power because not all the power from the battery goes to the load because you need this regulation element. And so again, the power dissipated in regulation depends on the current and also on the difference between the voltages. Okay, now once we have said some words about this is a general consideration. Okay, probably we will not find it in a book because sometimes I look at my circuits and say, why don't I try to see them on a different point of view? Okay, so probably we will not find directly this sketch or somewhere, I don't know. Well, this is the easiest way to implement a series pass regulator. The cheapest way. Okay. Don't be fooled by the number of components. The real components for a regulator are Q1, R, and Zener diode. The other stuff are just the parasitic elements that we always place in the circuit. In particular, I am supposing that this voltage is generated by a transformer, a filter, capacitive filter, and so at the end of everything we have a DC component in the output voltage, a ripple voltage, and we can consider the filament and also the diode resistance. Everything is placed here. And it's written here as well. How does the system work? Well, it's quite easy. Basically, if we consider V in as the sum of VDC plus V ripple, we can neglect, if we want, the filament resistance. It's not a problem. We can think that V in is basically on the collector of transistor Q1. What I do is, I take this voltage, and I simply make a standard voltage reference with the Zener diode. So the load resistance and the Zener diode. So at the end, I have a voltage which is fixed by the Zener diode. But I'm using this voltage as the reference voltage for the base of this transistor. In first approximation, you may suppose that the transistor doesn't take any current on the base, from the base, okay? But we know that if we connect the meter with a load, we are basically considering a sort of common collector configuration. Vuoi chiudere? Sì, c'è freschetto. Sì, invece il Covid ci becchiamo la polmonite. Sorry, it's too windy again. So in this case, if the transistor is working as a common collector configuration, I can say that the VB, again, is 0.7 volts. And so the output voltage is simply VZ minus VB. So VZ minus 0.7 volts. And the transistor will do everything that is able to do to keep its VB voltage close to 0.7 volts. Actually, the point that the base current of the transistor is small, is zero, is not true, because if we are taking a current from the emitter of the transistor, that's basically the same as the collector current, but we need a base current. The base current for this transistor is going to be IL divided by beta, the current gain of the transistor. So, in a second approximation, I must be sure that the base current of the transistor is not too large. It's not comparable, is much smaller than the bias current for the Zener diode. Otherwise, if I take too much current and I take more than the current that usually goes through the Zener diode can get out of breakdown, and I will lose the regulation again. This is not something so difficult to happen, because if I'm using this for a power supply, maybe here I want 1 ampere of current at least. Okay? I'm using this transistor here, but for transistors which are able to manage 1 or more amps, the beta is much lower, is around 20 to 50. So for instance, let's play with a beta of 50. 1 amp here means, divided by 50, means 20 milliamps of base current, which can be comparable to the bias current for the Zener diode. So when I choose the Zener diode and its bias current, I must forecast, I must think what will be the use for the transistor and how much current the transistor will supply. Pardon? See, okay. Well, your colleague was saying we can play a trick. The trick is to increase the beta using a Darlington transistor instead of a simple transistor. With a Darlington transistor, the beta is going to be 1000, and so that's true. Okay, but depends how much money we want to spend. In any case, okay, I would say that the word stinks, and then we know how to improve things, okay? But in that case, you are using 2 transistors instead of 1. Even if you buy it as a Darlington, it's more expensive, okay? So, let's see what I wrote here, but I don't remember. Okay, Q1 is connected as a common emitter common collector, or what we call an emitter follower. And you remember that emitter follower more or less is follower because the emitter follows the base signal. The emitter follows the base signal if you are considering small signals. But here we are in large signal. Basically, the emitter follows the base voltage minus VB. So there is tracking between the emitter and the base voltage, but we must take, for large signal, into consideration the VB, the base voltage. Okay. The output resistance, actually, here, should be quite good, quite low, because if you remember what is the, and I invite you, if you don't remember that, to look on the, for instance, the Cesar Smith for those formulas. If you consider the output resistance of the emitter follower of the common collector, we wrote formulas like we add the R pi, the input internal base resistance of the transistor, with everything that is connected from the base to the ground. Actually, on this node, we see R, but we see the dynamic resistance of the Zener diode that is certainly much lower than this. So basically, between base and ground, we see the dynamic resistance of the Zener diode. We add R pi plus this dynamic resistance, and we divide everything by 1 plus beta. So this means that if we have here 100 of ohms and beta is 50 or something like that, that we'll get an output resistance of the order of some ohms or even less. Okay. This is just a simple circuit. Actually, it's not very good for giving you large currents, but in principle, it can give you some large currents. Also consider that the R pi of the transistor is going to be low because, if you remember, the R pi resistance in a transistor is beta over GM. Beta is not very large, maybe 50, but GM is proportional to the current. It's 40 millisiemens for 1 milliamps. Here we are working with 1,000 milliamps. So the GM is enormous, and this means that the R pi will be very small. Okay. So actually, the output resistance could be very small. What about the thermal compensation for this circuit? Well, the formula is this. The output is Vz minus Vb. We know that if we increase the temperature, the Vb will decrease by minus 2.2 volts per millisecond, for degrees, Celsius degrees, okay. If we want that the difference remains constant, we must choose a Zener diode with a negative thermal coefficient 2, minus 2.2. So both terms will decrease with temperature and the difference remains constant. That's the reason why we prefer a 3.3 volt Zener diode for this circuit. If you use a 3.3 volts, the system will be stabilized. What's the output voltage in this case? 3.3 minus 0.7, that is 2.6. Well, is that useful? I don't know. Otherwise, if we want higher voltages, we must say bye-bye to the thermal stabilization. This is a very poor circuit, so just for if you don't have money for paying something more complicated, but we'll see how we can improve things. What I told you is basically said here. The variation of the output in terms of variation of the input. If you consider that basically what controls everything is Vz, well, you'll get the same formula that we found for a simple voltage regulator, reference voltage based on the Zener diode. So the formula is the same because all the variation on the Zener diode voltage will be on the output. So that's why we found the same formula here. I didn't calculate it again, it's just the same. About the voltage variation, depending on the current variation, is what I told you, the output resistance of this Q1, that is this formula here, what we wrote here. So the internal base resistance plus the resistance between base and ground divided by the beta. This circuit here works, but it has no intrinsic feedback. We can improve things if in some other way we measure the output voltage and we change a bit the transistor biasing. So if you can introduce a system for comparing, for giving a feedback from the output voltage and the reference voltage, we can improve a lot the performance of this circuit. So the circuit is fine, but there's no feedback. If you want to improve the performance, you must introduce the feedback. And we get to this one. It's a 2-transistor circuit plus 1 Zener diode, where we have the feedback. But I think that we need a fresh brain for, it's just 1 minute so we'll do that on Tuesday. It's Tuesday? Okay. We'll see that on Tuesday. Okay, so we can stop now, and I just want to wish you have a nice weekend, and see you on Tuesday. Okay? Bye-bye to everybody.